Hello, everyone. My name is Philip Tsai. Um, Welcome to the JPOMO pre-lecture. First of all, note that this meeting is being recorded, and the said recording will be uploaded to the POMO YouTube channel, which is this link for later viewing. Your YouTube, your video feeds and chat interactions in this meeting will not be shown in the public facing recording, etc., etc. And also, we'll go over the six sample problems, which are four short answer and two proof. Okay, and this meeting will be lasting from 7 p.m. to 8:30 p.m. Okay, so you'll go over the first problem if that is okay. So problem number one. A kinetic sculpture rests on three adjustable supports of positive lengths x, y, and z. For the sculpture to remain balanced, the supports must satisfy 2x plus y plus z equals 12. The sculpture stability score is given by x squared yz. Find the greatest possible value of the stability score. So does anyone have an idea how to does anybody know have an idea of what methods to try? Does anyone still have any ideas? Okay, I'll wait for derivatives. Yes, that could work. That could work, but there is a non-calculus solution to this problem that we can use. But derivatives are also a solution. Actually, um, I'll wait for like a minute for anyone else to give ideas. But you can message here in the chat. But for now, I'll just um write a general. I'll write up a right like um I'll make a write up of the derivative solution. So here's the first solution. Okay, so notice that the um since we know that actually it's 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 not the solution I have in mind about derivatives uses Lagrange multipliers. Now this is overkill, like overkill. But I think it's not a nice method to like first introduce people to, because normally with derivatives, there for this problem there are three variables. So that means even if you isolate one of the variables, like for example y is equal to 12 minus 2x minus c, then you still get an equation with two variables. So oh yeah, someone in the chat said EMGF. That is the solution. We'll get into that later. So for this solution, for Lagrange multipliers, actually wait no, I'll touch on that later. Actually, I'm not gonna do Lagrange multipliers then. I think it's more important to actually give the solution. So we're going with EMGM first, right? Here's the idea basically. Um, for AMGM in AMGM, the AMGM the arithmetic mean geometric mean theorem. I mean, no, sorry. The arithmetic mean geometric mean inequality says that for positive real numbers, a1, a2, etc. up to an, their arithmetic mean, which is basically the sum of all the terms divided by the number of terms, etc. plus a sub n all over n is greater than or equal to their geometric mean, which is basically the nth root of their product. So a1 times a2 times all the way up to an, a sub n. So how can we use this theorem in our problem here? Because here's the question. If we just use AFGM directly on 2x plus y plus z, we get 2x plus y plus z, right? 2x plus y plus z over 3 greater than or equal to the cube root of their product, which is 2xyz, right? But thing is here, this is not x squared yz. The 2 is here. It's not on the exponent. So this, we can't use LMGM here directly to find our to find the solution. So what does any of you suggest we do? Yes, Andrew. Um, we split the x into we split the two x into x plus x. Why? So that we can treat those x terms as separate in our um arithmetic mean, so that our geometric mean yields x squared instead of x, because now there are two x's instead of one 2x. It's a bit confusing to say, but you get what I mean when I write it out. So instead of three terms, there are four terms, and this instead is greater than or equal to fourth root of x times x, which is x squared, and then you multiply by y and z. Now notice by splitting the terms of x and x, you've effectively increased the exponent by one. And in fact, this is a very useful strategy for dealing with weird powers and with different powers from what would usually be in AMGM. But this is a very useful technique in um, many inequality problems. So here, we know that since 2x plus y plus z is equal to 12, this must be 12 over 4 or 3. So 3 is greater than or equal to the fourth root of x squared yz, and So 81 is greater than or equal to x squared yz, or on other words, x squared yz is sorry, x squared yz is less than or equal to 81. Now, are we done yet? That's the question. Because we have x squared yz is less than or equal to 81. But are we done yet? We have a upper bound for x squared yz. But again, um, we may or may not be done with this question. So, does any of you have any ideas on how to proceed from here? Yes, I like it. That's exactly correct. I'm sorry. So, um, we're not done yet because we don't know if there are actual values of x, if the upper bound 81 can actually even be achieved. So we need to check for values of x, y, and z that satisfy it. And notice, EMGM has default decays when A1 is equal to A2 is equal to A3, sorry, equal to A3, equal to A4, etc., right? So we need to check for this equality case. And if it holds true and this satisfies our equation, then we are done with the problem. So if we set x is equal to y is equal to z, then we know that x is equal to 3. Then we know that all of them are equal to 3, right? Well, this satisfies the first equation, which is um 2 times 3 plus 3 plus 3, which is 12. And also, this is the equality case for our inequality because x squared, I know 3 squared times 3 is equal to 3 to the 4th, which is 81. So, thus, this is our equality case, which works. And since we know 81 can be achieved, um, we know that 81 is our maximum value. So therefore, it must be the answer to this question. Speaking of questions, does anyone have any questions? Oh yeah, forgot the Lagrange multipliers. Um, it might be a little complex, and I might actually refer to a handout here. But basically, um, for Lagrange multipliers, we take partial derivatives. So, for, oh wait, wait, I'm going to refer to a handout for Lagrange multipliers because it's a very it's kind of an advanced technique. So if you're okay with so basically here the method of Lagrange multipliers is that yes, this is scary, but basically the essential concept of Lagrange multipliers is that we take partial derivatives um with respect to x, y, and z, or basically all the variables here. So in here, we first take the partial derivative of this, which is with respect to x, which in this case is 2. Yeah. Um. So we should first note that our f of x is the um it's the maximum value we want to find, which means that it must be x squared y z, right? And our g of x must be equal to 2x plus y plus c, right? So essentially, we take the partial derivative of 2x plus y plus c and x squared, which we take the partial derivative of g of x, right, with respect to x, y, and z, which means we have and then we multiply it by our Lagrange multiplier, which in this case will be lambda, I'm pretty sure. So 2 lambda, right? And then we take, and then we take the partial derivative with respect to x as well, which in this case must be, if I'm not wrong, 2xyz. And then we do this for all the other variables. So with respect to y, we have lambda is equal to, then we take this with respect to y, which is x squared d. And then we have we take it with respect to z, which means we have x squared y, right? And then all we have to do is solve this system of equations, and then that system of equations is yields the maximum an extreme value, which in this case must be the maximum value, because the minimum value, yeah. In this case, it's the maximum value. Actually, wait, yeah, because we can set one. If the minimum value, we know the minimum value must um be infinitesimally close to 0, 1. Yeah, just can just set y and be really close to 0 as as like 6, near 6. But either way, first we must solve the system of equations, and then after solving the system of equations, we must verify if it is a maximum or a minimum. If it is our maximum, then we're done. So in this case, um solve the system of equations. Wait, we Okay, actually, wait. Does any of you have any ideas how to solve the system of equations to get the values of x, y, and z? Just a small question first. I know we're getting a bit off topic from the sample problems here, but um, I think this is very interesting to talk about. And after that, I'll quickly talk about the other problems. Okay, in that case, um, we can divide the second equation by the, no, we can divide the second equation by the first to get the x over y over 2y is equal to 1 over 2, right? And so we get x is equal to y. And we can repeat this for x is equal to z as well because y and z is symmetrical. So we notice that x is equal to y is equal to z, right? And this is basically our the um same thing we did in the AMGM solution, but it's a lot faster, I'd argue, if you know how to take derivatives fast. So this is a very useful concept, especially in more advanced inequalities. But anyways, sorry for backtracking. We have question number two. Let ABCDS be a cyclic quadrilateral whose diagonals intersect at B. Suppose AB is equal to 9, CD is equal to 9, AD equals 16, and AC bisects BAD. Find AC plus BD. Okay, I will draw a figure here. Just wait. Just to actually no. I'll draw a figure here just to like make the viewing it like make it a bit easier, but to like visualize. But yeah, does anybody have any thoughts on how to approach this problem while I'm drawing the figure? Like, okay. So by the way, for geometry diagrams, it's usually very helpful to like um draw them nicely because it makes finding the angles a lot easier. I'm finding the oh yeah, sorry, forgot. Um, a cyclic quadrilateral basically is a quadrilateral that can be inscribed in a circle. So in this case, it would look something like this. I'm sorry, bad at drawing circles, but you kind of get the point. Like this. Yeah, it's a good drawing. So, oh, sorry, Andrew, I didn't read your message. So you can use the bisected angle to find the other length because they have people. Uh, yes, actually. So, um, for this problem, notice since they're inscribed in a cyclic quadrilateral, I'm sorry, no, sorry. Since B CAD subtends arc CD and the angle BAC subtends angle arc BC, right? And since sorry, an arc subtended by an angle must be twice that of an angle, right? So this is known as the, if I remember correctly, um, yeah, actually, it's a well-known fact that um, when angles sub is inscribed in a circle, that the arc subtended by the angle is um twice that angle. Yeah, basically. So for example, if I have an angle ABC, this arc right here has angle X, right? I'm sorry, has angle has um arc length. It's arc length and not arc. Has arc angle 2x. So in this case, since these angles are equal, we know since these arcs must also be equal. So this must be equal to this, right? And we can use it to find the other length. Okay, but how do we? What must be constructed to find the other length? So, also, sorry, it's a bit misleading, but anyways. So, does anybody have any um tip? Like, how does have any ideas on how to find the other length, which is BC, yeah? In this case, equal arcs towards. Yes, actually. Wait. Yeah, yes. They're actually right. Um, this is true. But what I was actually planning was for um to kind of prove this. It's like construct triangle BCD, yeah. Sorry for my bad drawing. And then realize since these subtend equal arcs, these angles must be equal. And in fact, since these angles subtend the same arc, they also must be equal. So all these four angles right here are equal. But that for the, for this, it doesn't really matter because we can now find the other length for BC because since these angles are equal, these sides must also be equal, which means this side length must also be 9. Now we still need to find AC plus BD, right? So how do we find how do we relate how do we use this information to find AC and BD? Actually, I'll give you a better question. Um, is there any relation between AC and BD? Yeah? Yep, Andrew, you're right. Okay, so Ptolemy's in this case is referring to Ptolemy's theorem, where if there's an ins where if there's an sorry if there's an if there's a cyclic quadrilateral A B C D, then AB plus sorry yeah um AB times CD plus AD times BC is the equal to the product of their diagonals. So sorry, plus AD times BC is equal to the product of their diagonals. So that is AC times BD. Now, I'm not going to go more in depth into this, but you can research about the Ptolemy theorem. Ptolemy theorem. think that's the name. I think I might have misspelled it, but okay. But this theorem helps us find the product of the diagonals. But how do we use this information? Well, actually, wait. This information will actually be used for later. So notice that 80 times BC is equal to 16 times 9, which is 144, right? Plus 89 times 9, AB times CD, which is 81, is equal to um AC times BD, which means that 25 is equal to the product of AC times AC and BD, right? Now, um, Andrew, you also said it's an isosceles trapezoid, right? That is true, actually. Again, what I was planning here was for congruence, for triangle congruence, but basically um we can prove that AC is equal to BD, yeah, through realizing that it's an isosceles trapezoid. Since you have to be a bit more rigorous, but since um this next um since this angle here is equal to this angle here by some angle chasing with us arcs, but also we can see that since AB is equal to BC equal to CD, right? Is equal to 9, right? Um, and we know that the angle CAB is equal to angle BCA, which is equal to angle BC, which is equal to angle BDC. Basically, yeah, we can prove by angle side or AAS or um SES or yeah, basically almost all we can prove using all the congruences that triangle ABC is congruent to triangle DCB. For this case, we can show it by AAS since angle CAB is equal to angle ACB, which is equal to angle DBC, which is equal to angle BDC, and since AB, again, since AB is equal to BC equals CD equals 9, right? So therefore, we can show that AC is equal to BD. And lastly, we can finish this off by realizing, yeah, by the way, we want to find AC plus BD here, which is basically equivalent to 2AC here, since we know that AC is equal to BD now. But basically, we can just substitute in AC is equal to BD here in AC times BD, and we get that AC squared is equal to 225, and we can just immediately concluded from that that AC is equal to 15, because of course a side length can't be a negative number. So therefore, since AC, we just need to find 2AC, we know that our answer, 2AC, is 30, and that is our answer. So, does anybody have any questions? Oh yeah, by the way, just like a side note here, you can also prove this using law of cosines and a lot of bashing, but it's very yeah, it's not particularly the most efficient way to do the problem because you're gonna have to like do a lot of algebra. So here is a more synthetic, but in other words, it's like use the normal geometric we use as little algebra as possible for our problem, the synthetic waves. Does anybody have any questions? Okay, I'll be moving on to the next problem. That's okay. So we have problem number three, which is from the JPOMO qualifying statement. Let A and B be positive integers such that the greatest common divisor of A and B is equal to 12. Suppose that the greatest common divisor of 3A plus 2B and 5A plus 7B is equal to 132. What is the smallest possible value of A plus B? Anybody have any ideas on how to approach this problem? Um, does anybody still have any ideas? Um, can we write GCD of A? Um, the GCD is the greatest common divisor. So since if we were to write it as AX plus BY is equal to 12, then the greatest common divisor of two numbers. Um, and we know that A and B must be greater than 12, right? Must be a multiple of 12. But here, if you were to write AX plus BY is equal to 12, we could theoretically assume that A is equal to like 3 and X is equal to 2 and what B is equal to 3 and Y is equal to 2 or something like that. But I'm not really sure of what you're talking about. So, and I think I appreciate the idea. I appreciate the idea. So, but yeah, I'm not really sure the how can proceed with assuming that. But nice try. Does anybody have any other ideas? Because I'm going to proceed with the problem. Okay. Um. Um. So my the idea here is to write um a is equal to 12x and b is equal to 12y. Why? No pun intended. Because now we have GCD, the greatest common divisor of 12x and 12y, 12, right? Well, we can deduce from this that um since 12x and 12y are somewhat are both submultiple of 12, they must those multiples of 12 must must have x and y co-prime. So in other words, the the greatest common divisor of x and y is equal to one from this. Because if it's not, then let's say 3 and 6, right? X equals to 3 and y equals 6. Then mean the greatest common divisor of 36 and 72, which is 3 times 12 and 6 times 12, right? That's not 12 anymore because now we realize that's just 36. 36 instead. So now we can we also need another technique from this for this problem, which is the Euclidean algorithm, which is a very, very useful technique for graded common divisor of large numbers. So in other in basically the essential thing with it is like you can sum for the greatest common divisor of x and y is equal to the greatest common divisor of say x minus y and y. Why? Because notice that the greatest common divisor divides both of these numbers, right? But so when you subtract them, it still becomes a multiple of the greatest common divisor. And same for here. And um say n is their greatest common divisor, right? So let's say actually yeah, let's say p is the greatest common divisor actually. Let let's say xp I'm sorry, no. Let's say np is equal to x and mp is equal to y, right? Well, um x minus y is equal to p times m minus n, right? Sorry, no, n minus. So notice that um the greatest common divisor is still the same because um if subtracting y from x from this um it can't change the greatest common divisor because y is already like the seventh thing, right? Sorry, I can't really describe it well, but basically that's how the Euclidean algorithm works. Anyways, we can basically subtract as many multiples of y as we can from x. So for example here, suppose that the greatest common divisor of 3a plus 2b and 5a plus 7b is equal to 132, right? Well, this is equivalent to um the greatest common divisor of we can subtract 3a plus 2b from 5a plus 7b. So we get 3a plus 2b, the greatest common divisor of 3a plus 2b, and then um 2a plus 5b, right? So, and then we can repeat the Euclidean process again. So we get, um, we basically just want to clear out one of the terms so that we get a cleaner expression. So this is equivalent to the greatest common divisor output, a minus 3b and 2a plus 5b. And and lastly, we get this is equivalent to the greatest common divisor, um, 11b and a minus 3b, right? Well, how can we use the information that, how can we use the substitution of a equals 12x and b equals 12y to our advantage? Well, here we know that it's equal to 132, right? We can basically divide up, we can basically substitute first 12x and 12y here to get that this is equivalent to the greatest common divisor of 12x, 12 times x minus 3y, 11 times 3, 11, 12 times 11y, right? And then we can kind of um divide essentially everything by 12. So from like a similar reasoning for why this is equivalent, so we get the greatest common divisor of x minus 3y and 11y. Okay, yeah, wait, sorry. Uh, yeah, so this is equivalent to 12. Wait, sorry. Yeah, wait. Make a mistake. Oh yes, 11. Sorry, it's equivalent to 11 because we divide by 12. So realize, okay, um, this implies since x minus 3y is a multiple, sorry, is a is a multiple of the greatest common divisor, which is 11, x minus 3y must be a multiple of 11, which we can represent in modular arithmetic. And then we can test values of x and y to find the smallest possible value of a plus b, since a plus b is just essentially 12 times x plus y, or 12 times parentheses x plus y. So since x is equivalent to 3y mod 11, we can just test out the values of x and y here. So for example, we can see that but the thing is also we have to take note the great x and y must be co-prime. So that means they must not have a greatest common divisor above one as well. So in this case here, we can see that 1, 4 works here. Actually, yeah. Actually, yeah. Um, yeah. But we have to also test out other values of x and y. So in this case, we have also we can increase or decrease y by 11 or x, but we're testing out values of x. So we only care about what y is going to be. So it's not really four. It's to describe all possible x here. We do 4 mod 11. Why can be 4 mod 11? Because after 11, it just repeats. The remainder repeats. But anyways, um, we test out other values of x. For example, 2. We get that when we plug in x equals 2, we get that y is equal to um, is equivalent to 8 mod 11. But this, even with a small value, a possible pair, comma 8, we still um get a possible value of a plus b greater than 1 plus 4, which is 5. So will will still yield the smallest possible value. But we also have to test other cases. For example, plug in x equals 3, then get y is equal to 1, mod 11. And actually, wait, no, sorry. This also doesn't, by the way, this also doesn't work because um, x and y are not co-prime, or basically their greatest common divisor is not equal to 1. But here and here, seem like really promising cases. And this actually yields a smaller value than this, which is um, 4 times 12, which is 48. And actually, this must be our answer for a plus b. Sorry, yeah, this must be your answer for a plus b because if we go, if we plug in x and y, if you plug in x above 3, then notice our value must always be greater than um our a plus b must be greater than 48 because this must be a y must be a positive integer, and so this must be greater than x plus y must be greater than 4, which means a plus b must be greater than 48. But anyways, so from this, we conclude that the greatest possible value was 48. I'm sorry, by the way, for my kind of messy explanation, but I hope you get the gist of what I'm trying to explain here. So basically, we will use the Euclidean algorithm to find that our greatest common divisor is our expression here is equivalent to this expression. And then we sub in a equals 12x and b equals 12y to get rid of all the factors of 12 and all the multiples of 12, sorry, which is helpful because now we can just test out values of x and y, find the smallest possible value. And actually, I think it'll be helpful for us to actually plug in the values here. So for example, in this case, a is equal to 36 and b is equal to 12, right? Well, their greatest common divisor is 12, and their greatest common divisor here is 12 times 12 times 9. So it's 132, and then 12 times. I'm basically just factoring out the 12 up here. So it's 15 plus 7. So we just get basically the greatest common divisor of 132 and 4, which is also 132, which is 132. So our tested values actually match the expression. So we're kind of done. But anyways, um, I'll be moving on to the next column because we're kind of running out of time. So question number 4. A dart is thrown uniformly at random at a circular target of radius 100. Targets divided into 100 rings of by circles of radii 1, 2, 3, 4, 5, 6, up to 100. Each one fully in all circles which are larger. Starting from the center, the rings are alternately assigned a score of positive 1 and negative 1, which with the innermost disk assigned positive 1. The expected value of the score for random throw can be expressed as m over n, where m and n are relatively prime integers and n is positive. Find m plus n. So I'll just draw the diagram here. So here we have actually with any geometry problem, it's very helpful to draw a diagram first. So here, um, we have the target divided into 100 rings. So it's something. It looks something like this. So it's 100. I can't draw 100 rings, of course, but I can draw a relative definition of what it looks like. So this is a circle with radius 2. This is a circle with radius 1. And this is the circle with radius 3, etc., etc., right? All up to 100. Sorry for my bad circle drawing. This is also very exact. This is also very under exaggerated. Anyways, this is we must have. I'm going to shade all um scores at side one with positive one with black. Okay, so it's something like this. So circle with radius 1, for example. Um, just pretend this is black. Okay, so it looks something like this, and then we go on and on and on and on, all up to 100. So um, first notice that um the expected that we need to find the expected value of the score, which wherein the expected value is basically um sorry, the expected value is basically the probability of its outcome. So the expected value is basically if P1 is the probability, so the probability of its outcome multiplied by sorry, the probability that you will achieve its outcome multiplied by what's more the prob what you get from probability. So here, and then you just add them all together, all possible probabilities, all possible, basically all possible things that can happen. So if S is the score or to receive and P wants a probability, then it will look something like this. A probability or expected value looks something like this. Sorry for my bad handwriting. All up to P100 times S100. It's because we have 100 grades here. So basically, our score in this problem is positive one and negative one, basically where it alternates for odd and even integers. So here we must have a positive P1 minus probability. By the way, P sorry, I haven't defined what P1 and P2, P3, P4, etc. is yet. But let's say probability one is for outcome one happen, which we will define here as the probability that the dart reaches the hit the circle with hits this spot. Basically the circle with radius one. And then as it goes on, the P2 is here, P3 is probability of hitting here and etc. Why are we doing this? Because this is basically the definition of what the expected value is. So we need to like define what we're trying to get first in a problem like this. But anyways, um, does anyone have any idea of how to get a probability for each um for to hit each um part of the part of each ring? Sorry, to hit each ring. Basically, yeah. I'll just restate the question. Basically, does any does anyone have any way to find P1, P2, P3 up to all up to P100? Um, okay. Since we're running out of time, I will demonstrate a solution to this, right? You can still comment your ideas though as we go on. So here, the probability of hitting ring one, which basically is the innermost circle, is 1/10,000, right? Because 10,000 is the area of the whole um target. So that's basically the probability of that. And then you have to subtract the probability of reaching this this section here, which this ring here, which is which is with, wait, sorry, I'll rewrite, redraw it. So that's essentially um the probability of reaching here, right? Which is this entire circle minus the area of this circle. So in this case, yeah, this entire circle minus the area of this circle. So in this case, it's a circle in all of the rings actually. It's the difference in area between circle n plus one and circle oh sorry, no, it's not 1/10,000, sorry. The probability is 1/10. So it's actually, yeah, it is 1/10,000, sorry. But it's 1 pi/10,000. But all the pi's cancel out each other out in the solution. Well, so sorry, I will not mention that. Oh, Andrew, yeah, you're right here. So, but basically, it's n minus one plus n minus n squared for the area of each ring. And where do we start um from this ring here, from this ring here? So after 1/10,000. So this we can simplify this to n squared plus 2n plus 1 minus n squared by the square of a binomial. So we can simplify this basically to just 2n plus 1. And since we start from n equals 0, which is basically just the area of this circle, we go up from there. So we have the area of this region being um 3 pi, or basically a probability of reaching this of hitting this ring to be 3 over 10,000, and then we add 5 over 10,000, and then we subtract 7 over 10,000. I think you know where I'm going with this. All the way until we go to, well, when did this end? Well, in the 99th circle, sorry, it's definitely not George scale. But anyways, um, for this last region here, it's a difference between the areas of circle 99 and circle 100, right? So we stop at the 100 squared minus 99 squared pi, or in other words, we stop at sub sub nine 199 over 10,000. Now it out. So we can just focus on the numerator. It's 1 minus 3. So the numerator is 1 minus 3, sorry, minus 3 plus 5 minus 7, all the way until you add 197 and subtract 199. Basically, you're just subtracting and adding and subtracting alternately the odd positive integers and the odd integers. So um here here um you must you can actually group 1 minus 3, 5 minus 7, all the way until 197 minus 199 here, just like how Andrew did it. Thank you, Andrew. And so we get negative 2, and we just get a constant term. Well, if we group them, then we just get negative 2 minus 2 minus 2 minus 2, all the way until we get to 197 minus 199, which is also negative 2. So we just get a bunch of minus 2's for our numerator. And how many negative 2's in fact we get? Well, we can start from, I also start from the end term. I'll just count from the end term. So we got 4 times 1 minus 1, and then we have, basically we're just counting how many groups we have of 1 minus 3, 5 minus 7, etc. All up until 4 times 50 minus 1. So this each of this, 4n, each 4n minus 1 counts the number of groups I like to call them. So since there are 1 up to 50, there are 50 groups. So the numerator here is negative 2 times 50. Yeah? So we still have the denominator of 10,000, and then we does have a probability, or we have an expected value, sorry, of negative 1 over 100. Notice that expected values can be negative if you're basically inherently losing from throwing a dart. So our expected value is negative 1 over 10,000. I'm sorry, negative 1 over 100. And it must be expressed as m over n, where m and n are relatively prime integers, and n is positive. So this is our last two here. So since the expected value is negative 1 over 100, the denominator cannot be negative. So the numerator must have the negative number, which is negative 1. So m plus n, therefore, must be 100 minus 1, which is 99. Sorry, Corbin. Which is 99. So sorry for that long talk, but basically, just to summarize everything, we um realized the expected value was the an alternating difference and sum of the probabilities. And then we calculated these probabilities individually and then notice a grouping pattern where there's just a bunch of negative two. So three grouping, right? So thus we found the expected value. Does anybody have any questions? Because we're gonna start moving on to the proof problems. Yeah. Okay. So we're now proceeding to the proof part of this um lecture. So we will be discussing the introduction solution writing. So um here's a question. Say you were given two proofs such that the sum and the say you're given two proofs that the sum of two even integers are also even. So we are given two solutions here. So which solution would you rather read and why? By the way, you're free to chat in the chat box. Okay. So um, does anybody still have any answers? Oh, Andrew, yeah, and Aries also yes. They both answered chubby, but why not Penrick? Why not? Why is Penrick's solution worse than chubby? So this is that's true. 8 plus 8 is not equal to 67. But that can just make the solution Penrick's solution worse than chubby. So So in this introduction, we'll be detailing a bit more specifically on how Chubby's solution is better than. And I know you already have some answers here, but I'd like to um give some more examples and give some more criteria on a good solution. So in the JPOMO final stage, you'll be writing full solutions for two of the questions that are 16 and 17. So someone else is going to read your work. And since you're writing solutions as a submission for a contest, it is usually fine, right, just enough so that the grader can understand your work. How much is just enough? Well, usually just usually it's better not to be like over elaboratory or basically things that you can just calculate without much thinking. Things you don't really need to calculate without much thinking. You can usually just um not put it in the solution because it saves time. Number one and number two, because if you put too much, then it might be your solution might be wordy, maybe hard to understand. So the first criteria is to be crystal clear. This is very important for especially for those who have bad handwriting like me. So we have to write legibly and in sentences. So number one, and even though you're running, but if you're running off time, again, it is. I'm sorry, not again. It is okay to not write the full parts, especially calculations in sentences, as long as what you're writing is still clear. Also, clearly define any new variables or terms that you will use in your solution. So, for example, let instead of saying let a and b be two numbers, you should say let a and b to be even integers. Why? Because numbers is very unspecific. It's not specific. It doesn't. It's not like in a sense. It doesn't. Um, for the person who's going to read it, they don't really know what you're exactly talking about, which can make the solution confusing or even like wrong in some parts. So it's very important to clearly define any new variables or terms you will be using. Sorry, I say that again. Also, you have to explain your reasoning. Proving or showing a statement means giving a full explanation on why it is true. In Penchick solutions here, for example, they just this they just listed an example. For example, 2 plus 2 equals 4, 2 plus 4 equals 6, etc., etc. And the pattern goes on. But the thing is, they haven't proven the pattern goes on. So that's not a full proof. Like Chubby, who proved it generally for the general case. So it is like like what I said earlier. It is not giving examples that support a statement. It is proving that the statement holds for all of the specified conditions. However, if the question asks you what if the question asks you to prove something that exists, then it will be fine to provide examples as long as you show that the examples satisfy the given conditions. For example, prove that there is a natural number that's divisible by 2 and 3. In this question, we only need to find a natural number that is divisible by both 2 and 3. And then and afterwards, we just need to show that it is indeed divisible by 2 and 3. For example, this, this is already all right because we cited the number, we cited the number, which is a natural number, and we showed that it is divisible by both 2 and 3. Of course, proofs for actual problems will likely be much longer than this, but it essentially follows the same formula. Also, it is very, very necessary to write correct math. Even one small mistake can affect the rest of your solution. For example, okay, usually in contests, um, even one small mistake, like even if like you make like a small math error, that can be a difference between a full marks and like for example 10 points and like 7 or 6 points, like 7 points or something. Right? Just one small mistake can affect like a lot of points basically. If you still have remaining time in the contest, it is always worth it to check that everything you wrote in your solution is correct and that you made no small errors like typos. So, for example, Penrick here writes number, but instead of the proper word number, unlike Chubby, who writes in legible, um, correct English, which makes it much easier for the grader to understand. Also, for Also, another reason why one small mistake can really affect the rest of your solution is because um it kind of works like a domino effect, where you're proving another statement on that small mistake, which can really mess the rest of your solution up if you're assuming the wrong things, if you're proving the wrong things. It's also a very common mistake to write in the wrong direction. Do not write proofs backwards unless you know what you're doing, because this means that, yeah, and writing proofs backwards means that the proof goes on from what is being asked, something that's known to be true, instead of what what you should write instead is proving something that is known to be true. I'm giving something that is known to be true and manipulating it and using it to show that the what is being asked is true. This is incorrect because if A then B does not always mean if B then A. For example, okay, all squares are quadrilaterals, right? But not all quadrilaterals are squares. So if I'm asked to show a proof that all squares are quadrilaterals, I cannot start from a quadrilateral because that's that cannot always already be a square. So here's an example here. Here's the AMGM inequality for two um two numbers instead. So prove that for positive numbers A and B, we have A plus B over 2 is greater than or equal to the square root of A times B, right? This solution is wrong because you start from the given. If I'm sorry, you start from what you need to prove, A plus the AMGM inequality, and then you proceed to a true statement. Instead, a correct way to write it would be starting from a true statement like A minus B squared is greater than or equal to 0, and then proceeding to the AMGM inequality. Also, here are some other types of problems. If a problem asks you to find all objects that satisfy a certain property, you must state what these objects are, show that they satisfy the property, and show that there are no other objects that satisfy the property. So, for example, if a problem asks you to find all even integers, then you must first state that they must be. I'm sorry, no. If a problem asks you to find all even positive integers, then that you can just then you must first state that they must be 2, 4, 6, 8, etc., etc. And then after that, show that 2, 4, 6, 8, etc., are indeed even positive integers. And then lastly, show that there are no other even positive integers that are not included. And if the problem asks you to find a minimum or a maximum value for a certain quantity y, then you must state what the mix. Number one, state what the minimum or maximum value is, and then show that the value is attainable. And then lastly, show that there cannot be a value lower than your answer or higher than your answer, which means a value more extreme than what you're trying to find. Actually, we already have an example of this type of problem, but it's not a proof problem. But even then, we still showed it, which is in this case problem number one. So what should we find? Well, stated what the minimum or maximum value is, which is 81, which is our maximum value, and then um we show that the value is attainable by setting x equals y equals z equals 3. Yeah? And then lastly, we also show that there cannot be a value higher than our answer because it's the greatest possible value. In this case, by using the AMGM inequality. So if we forget these pointers, do not worry. The proof, but by the way, you don't need to like memorize them. You just have to like learn them. You have to learn them by you can just learn. It's better to just learn them over time because then it kind of it's much easier. It's like you learn a lot more. And not it's yeah, it's much more helpful to actually understand what they mean, why these conditions are the case. So if you forget these pointers, don't worry. The proof questions in the JPOMO final state will include these to guide. And also for more comprehensive tips, you can check out this link right here. Um, Although the examples shown there are more advanced. Enjoy smooth writing. Yeah, I will. By the way, I will send the link in the chat box for anyone who wants to read after. But yeah. Anyways, so we're kind of out of time here, but I'm going to do a quick skim of each food problem if you're fine with extending a bit. So problem number five, we have that n factorial equals the product of all integers, all positive integers for it, and up to it. And then so we have okay, prove or disprove. For every integer n greater than one, the rightmost non-zero digit n must be even. So in this case, um, also by the way, for the proof problems, if anyone has like a solution to any of the problems here, you can type it in the chat box. You're feel free to do so. So notice we can prove this by induction. Actually, we can prove that this is true by induction. So a good way is just to start. We can prove this. Um, can start by um. By the way, even if your handwriting isn't the best, it's okay to. I mean, even yeah, it's okay to like uh, um write in. It's still okay. It's okay to like write slightly messily, but as long as the grader can still understand your solution. Okay, so can prove this. So we can start by the statement. We can prove this by induction, right? And then usually we say proof, and then we give our proof by induction. In this case, we start with base case n is equal to 2, which is factorial n into. And since we only need an example here, since any post-exclusive example, Um, we only need to show that it ends in an even number, which we already showed. It ends in two, since it's exactly two. And then we have the inductive step for induction. Basically, the inductive step is showing that if n satisfies the condition, then n plus one also satisfies the condition. This induction is a very useful tool for many problems, including this. So in this case, yeah, given that n factorial ends in even number, an even number, then sorry for my bad, then we must have then we can multiply then n plus one factorial. Now we only need to prove that n plus one factorial. So given that n factorial is at n ends in an even number, we must prove that n plus one factorial also ends in an even number. And basically, this is all we need to prove for a solution. Now, I'm going to skim through this, but basically, just since n factorial ends in an even number, it's it it must also be an even number, right? So, actually, no. Right most non-zero digit, right most, sorry, right most. But anyways, it's not even, sorry, it's not even, sorry. So, if it's, if you move all of its zeros, it still is an even number. So, if you multiply by another number, um, you still get an even number because an even number times anything is an even number. Yeah, an even number times anything is still an even. Any real number is still any positive. Like, an even number times anything is still an even number for this case, for this problem. So basically, yeah, that's the outline of our solution. And for, by the way, we call these subtasks. For subtask B, we have to determine all digits such that there exists infinitely many integers and for which the rightmost ones are the different factors. For example, okay, um, 2 factorial, the rightmost digit of 2 factorial is equal to 2 because 2 factorial is equal to 2, right? So, so we need to find in, we need to prove, we need to show that which integers and which digits, sorry, which digits x um have infinitely many integers and with this property here. So yeah, that's basically what we need to do. And in this case, just um in this from the solution is yeah is I'm pretty sure it's 2, 4, 6, 8. Someone correct me if I'm wrong, but if I remember, it's the solution is the answer is 2, 4, 6, 8. It's usually very helpful to state it's important to state the answer first for like a find all question so that it's more organized. Anyways, so our answer is 2468, and then we have options here, which is basically finding which um which is basically showing that um um like finding construction where we can generate infinitely many integers and or with that ends with one of these digits. Since since I have to skip to this already 847, I'm just gonna go on to the other proof. So problem number 6. So intuitively, you might think the answer is 10 because it becomes 30, but no, actually, the answer is the square root of 102. So you have to state the answer first, square root of 102, and then we have to prove it. And actually, I want to change the question a little bit, okay? To just remove some vagueness. It's not, it's kind of inside always greater than the South class because the amount of Penchicks that leave and enter the shop kind of varies over time, right? So it could go up and down, up and down. So better to give statement here. Anyway, so it's better to be specific even in the problem question. So anyways, um, proof here is that first we show that the um spread of 102 satisfies the condition here. And since after how many minutes, it's actually all basically we, we have to show that for all to be greater than 100 square root of 102, the amount of penchicks that are in the shop are greater than 30. And so, firstly, you have to show that the square root of 102 works in this manner, and then prove that any number below square root of 102, you'll still get um a number of penguins, sorry, not penchicks, that it's that is greater than or and less than or equal to 30. So I'm going to go with this first part here. So it's the number of penchicks that leaves us that enter the shop is squared is the floor of t squared over 2. Basically, it's the greatest integer less than or equal to a number. And then the number of penchicks that leaves the shop after 3 hours is t squared over 5, which means that this is the expression for the total number of penchicks at any given moment. Penguins. Sorry. So um at square root of 102, we get third actually it's greater than what matters. it's infinitesimally close to square root of 102. This means it's square root of 102. Anyways, sorry. So square root of 102, it's um 51 minus 20 minus 28, right? Because it is something this is 102/5, right? Which is in between 20 and 21. So this is just equal to 31 Penchick. So penguins. And realize that if you increase square root of 102, the next change in the number of penguins is square root of 104, which is an increase in penguins, which means there'll be 32 penguins. And then square root of 105 and square root of 106. Next change. So it goes from 32 back to 31, and it goes from 31 to 32. And since there it and it kind of like goes in a cycle of sorts. So where um increases. So um it tends like we cannot just say it tends to be. We have to prove that it increases above 30. It stays above 30, yeah, after from that point on, right? But, well, um for any even integer, for any square root of n where n is an even integer, the thing goes up except if it's 10 where it's safe. Where it's a multiple of 10 where it's safe, right? In the same spot. So, and since you will always find one even integer in between a multiple of 5, two multiples of 5, um, it'll always tend to like it is guaranteed to go up and down, go up and down at least once before going up again. And so it always tends to increase. I mean, it always tends to at least stay the same or increase. And so after that point on, it will tend to it will be greater than 30. So square root of 102 works. And now you have to prove that square root of 102, any integer less than square root of 102 doesn't work. Any positive real number. Sorry. Oh, wait, sorry. It's not square root of 102. Sorry. It's square root of 102 times 60 because it's minutes. But that doesn't matter here. So imagine, yeah, for access less than square root of 102, notice since it tends um as square root of 100, if you go even just a little bit below square root of 102, you already get something equal to 30. So that's already um enough for the shot that's already that the shop can already can still handle that. So if it's any x less than square root of 102, you even like infinitesimally less, as long as less than square root of 102, it will be it will have some x and um like square root of 102 minus epsilon, if you're familiar with that. epsilon is infinitesimally close. Um, you still get something slightly less than 102 here, and slightly something less than 102 here. So this is 20, and this is 30 still. And no, sorry, this is 50. So it's 50 minus 20, which is 30. Sorry, it's 2. So if you have any number less than square root of 92, any positive real number, um, you get you'll eventually any number slightly you'll find a number slightly greater than that. Infinitesimally greater than that, and has 30 Penchicks. And that's 30 penguins. So yeah, that's basically the outline for the solution. It's not the actual solution itself, just an outline because we have no more time. So yeah. Does anybody have any questions before we close? We'll end by 9 o'clock. Okay. So I'm just going to close off by stating that the recording of this lecture will be posted shortly on my YouTube channel. It's Penchick POMO. And also for those joining the JPOMO final stage, please be sure to read the content finder, which can be found at this link right here. I'll send it. But basically, that contains all the details you need to know about the JPOMO final stage. It's happening in 3 days. Nice. So yeah. Um, Again, does anybody have any questions about the problems here? Because I'm, because yeah. By the way, Kaiser's sent the um link to the JPOMO contest banner, which in the chat, in case you need it. Okay. In that case, um, I'll be, we'll be. I think we're done with the lecture. So thank you all for running the lecture, and I think you can. I'm pretty sure you can all leave now. Um, Good luck for the JPOMO final stage final for those who are joining.